Hi, everyone. Uh, okay, so today I'm going to do two questions on rotational motion. And I actually had a third question, but I don't think I'll be able to fit it in. I'll just mention it to start with because it's pertinent to your third test. But we actually did one very similar to it. During the live stream the week before the break. So I don't see a purpose to redoing that. Rather, I'm going to do two other questions, okay, in rotational motion. And the only other thing is, before I start, is the test. It is 32 points. I just looked, and it's the same format as before. You're the 1020 class. I'll actually allow it, make it available at about 9:20 in case you have some conflicts with other classes. You could start it an hour early, but it actually doesn't matter when you start it. You could start it even after 10:20, though not too much after 10:20, because eventually I will close it up again. But you'll get 2 hours. Okay, that's the maximum allowed time. Okay, and well, that's it. It's open book like the other ones, but don't talk to anyone. Okay, so let's start. Let me just show you the first question. Actually, it's a pair of questions, but they're closely related. But like I said, we did these already, and you had one like it in your on your assignment, so I don't see a point in redoing it. But just to refresh your memory that you do need to know how to do questions like this. This is basically a ball of a certain mass and radius rolling downhill. Now, I think before we did instead of a ball, we did a drum. And so the formula for the moment of inertia is different than it is for a solid sphere or a ball. But other than that, I mean, it's pretty much the same, and the numbers are different. Okay, so basically you have a ball that rolls downhill, and at the top of the hill, it's all potential energy, mgh, and at the bottom of the hill, it's all kinetic energy. But now the kinetic energy is in two types. It's translational kinetic energy, 1/2 mv squared, and it's rotational kinetic energy, 1/2 I omega squared. And there is a relationship between v and omega, the velocity of the center of mass, and omega, the angular velocity, and that's the relationship for rolling. Okay, and that is that omega is equal to rv, or no, sorry, omega is equal to v over r. Here, I'll write it. I actually said it wrong. This is the condition for rolling. V is equal to omega divided by r, like that. Okay, and you make use of that, or no, I did it wrong again. Geez. Omega is equal to v over r. There we go. This is correct. Sorry about that. Uh, So, you make use of that to basically eliminate the omega in terms of V, and then you can solve the problem. Like I said, I did one like that, so I don't see another reason to do it. And then I ask questions like, what's the total energy at the bottom? Well, that's the total energy at the top. What's the translational kinetic energy? That's just the 1/2 mv squared. What's the rotational kinetic energy? That's just the 1/2 I omega squared, but using the rolling formula to convert back in terms of V. Okay, what's the total energy? What's the velocity at the bottom, and what's the angular velocity at the bottom? And they're not necessarily answered in that order. Okay, so anyhow, there it is. All right, let's do this problem right here. Okay, this problem is basically a tau is equal to I alpha problem. Okay, so it's a actually rotational dynamics. If you remember, tau is equal. No, that's not it. We did a tau equals I alpha. Sorry, guys. Yeah, we did a tau equals. Yeah, we did that already. No, this one is a number 6 is. Here we go. We want to do this one. There we go. Okay. That's the tau equals I alpha problem. I'm sorry, guys. I'm a little bit. I'm going off of notes I made yesterday. Okay. Anyhow, so this is a tau is equal to I alpha problem, and that's like F is equal to ma, but for rotational motion rather than linear motion. Okay. And so, well, let's do it. Okay. So I have a rod, and it's of length 1.2 meters, and it has a mass of 3 kilograms, and it's free to rotate around its center. Okay. Now, that information gives you enough to calculate the moment of inertia, okay, which is the first question you see there, moment of inertia, all right? And just to remind you how you calculate moment of inertia, the moment of inertia, I gave you quite a few formulas, okay? It depends what your situation is. In one situation, you might have just some point masses, okay? So, like either in a line or in a two-dimensional plane. And in that case, if you have just these point masses, the way you calculate it is mr squared for each of the masses and then add it all up. So like mr squared for the first mass plus mr squared for the next mass plus mr squared for the next mass and so on. But sometimes you have, shapes like spheres, like in the problem I just mentioned, or rods like this one. But for the rod, we actually have two situations. We have the rod where it's free to rotate around the middle, and that's one formula for the moment of inertia. So you can picture my remote here like this, maybe you can see it better that way. You can see my remote, and like that's like a rod, but now see how it's free to rotate around the center there, which is this situation, and that's one formula for the moment of inertia. Or the other possibility is it's a rod, but it's free to rotate around one of the endpoints like that, okay? And that's actually a different formula for the moment of inertia, okay? So I have a rod, I give you its length, I give you its mass, and I tell you that it rotates around the center, okay? And then I can ask the question, what's the moment of inertia? All right, so how do you do that? How do you get that moment of inertia? Well, the formula for a rod rotating around the center is I is equal to 1/12 ml squared, okay? And the mass I tell you is 3 kilograms. The length is 1.2 meters. And so it's very simple. It just turns out to be 0.36 kilogram meters squared. Okay, so let's continue reading the problem. It's initially at rest, all right? And we apply a force to it. And we apply the force at 20 centimeters from the center, okay, at an angle of 45 degrees, okay? Now that might be a little hard to picture, and so I'm going to draw that for you next. But basically, what I'm giving you there, the information I give you where I say we apply this force at a certain distance from the center and at a certain angle, I'm giving you torque information. Because the formula for torque, the formula that relates torque and force, is this formula right here. Oops, why am I? There we go. It's this one right here. All right, tau is equal to RF sine theta, okay? And so that information gives you enough to calculate the torque. Let me, I mean, you probably don't need a diagram. You could just plug in the numbers, but let me just draw it for you so you could see what I'm talking about. And I lost my, oh no, it crashed. Okay, hold on a sec. I'll get it back up. My other drawing program. This shouldn't take long. There we go. Okay, so and let me switch to 100%. Okay, so basically I have a rod, and so you can picture the rod like this. Okay, like that. and I tell you that the rod is free to rotate around the center. So there's the axis, but it's actually like going into the board, so that this thing is free to rotate like this. Okay, it's actually free to rotate in the plane of your screen like that. Okay, and the whole length of the thing is 120. So this length from the edge to the middle is half of 1.2, 120 centimeters or 1.2 meters. It's 0.6 meters like that. Okay, but we don't even apply the force at the edge. Okay, I say we apply the force at 20 centimeters or zero point 0.2 meters. Okay, and so I guess let me do that in purple here. It doesn't matter which side because this thing is symmetrical. So let me do it on the right side here. So starting from the middle and then moving out 20 centimeters, I'm going to apply a force right there at that purple dot right there. Okay, and it's 100 Newton force. But how do I apply it? I don't apply it straight in like that. That would be 90 degrees, okay? Because let me draw in red here. Like there's like a radial vector. That's the vector. That's the r vector from the axis to where you apply the force, okay? And if you ask, what's the angle between that radial vector and the force? That would be 90 degrees. But I said, no, this isn't being applied at 90 degrees. If you read the problem, I said it was being applied at 45 degrees. So let me erase that. Okay, actually I'm applying the force something like this, 45 degrees like that. Okay, or I guess like this. Okay, actually it doesn't matter, to be quite honest. It doesn't matter whether the 45 degrees is on this side or the 45 degrees is on the other side. Okay, it doesn't matter. Now when you have a torque, so the formula for the torque, let me just rewrite it here, is equal, r is equal to, sorry, tau is equal to rf sine theta, like that. There are actually three ingredients that go into calculating the torque. Of course, the force. So the harder you push, the faster this thing is going to turn. That makes sense. The other one is R. The further out from the middle you push, the faster it's going to turn. If you were to push like straight on the axis here, I don't know if I can even draw it, but like, you know, well, let me draw it on the top here. If I push on the axis there, I'm not going to be turning this thing at all. That's like on a door. If you push on the hinges, you're not going to turn a door pushing on the hinges. And so you want to push as far from the middle as possible. So if you were to push all the way here at the tip, that's the biggest R you get, and that's going to be the biggest torque. Okay, that's why your doorknob is on the other end from the hinges. Okay, you want to put your doorknob as far from the hinges as possible because that's when you get the greatest torque. Okay, so that's another ingredient. And then the third one is the angle here, and the angle is if you push at 90 degrees, that's when you're going to get the biggest torque. If you push at an angle, you get less of a torque. And if you like pulled straight out, like suppose you or push straight in, suppose you push straight in, that's not going to turn it at all because you're just pushing straight into the hinges, okay, or into the axis here, and that's not going to turn it at all. So the bigger the angle, well, not the bigger the angle, the closer the angle is to 90 degrees, the more torque you're going to get. Okay, so those are the ingredients that go into torque. Let me switch back to this whiteboard here. And so over here we have that the torque is equal to r of sine theta. Okay, and what did I say r is? Well, you know, the most it could be is 60 centimeters, but I've actually said, no, we're pushing at 20 centimeters. So that's 0.2 meters. Okay, so the r is the distance from the axis to where you apply the force. Okay, and that's 0.2 meters. How big is the force? F, that's 100 newtons. Okay, and at what angle am I pushing? I told you it's 45 degrees. Okay, and then if you just work that out, that turns out to be this number here, which I would round off to 14.1 newtons. Okay, so that's the torque. Now what do we have? We have the moment of inertia, we have the torque, and what's the next thing I can ask? Well, think of tau equals I alpha as the rotational equivalent of F equals ma. Okay, so you know, mass is mass. Its rotational equivalent is I, the moment of inertia. So these two are like an analogy to one another. Okay, and a is the linear acceleration, and what's its angular equivalent? Well, alpha, the angular velocity, sorry, the angular acceleration. And then what about the force? What's the angular equivalent of the force? It's tau. So tau equals I alpha is Newton's second law, but recast into rotational motion. Well, we have tau and we have I, and now if I ask what is the angular acceleration, tau alpha is equal to tau over I. Just plug in the two numbers and you get this value right here. Okay, 39 point whatever, it rounds off to 39.3 radians per second squared. Okay, And that would be the answer. Now, I just want to say one thing about radians because that's going to come up in the next couple of questions. Um, a radian, you might say, where's the radian in the units here? Because if you take a look at the units of I, they're kilogram meters squared. Okay, and if you take a look at the units of tau, they're Newton meters. Okay, technically speaking, a Newton meter could be written as a joule because it's Newton meter is also a unit of work, but no one ever writes it as a joule because it just looks funny to write a joule for torque. It's a Newton meter because remember, torque is a combination of force and distance. Okay, so Newton meter like that. Anyhow, a bit of an aside, but you see, you have kilogram meter squared here, and you have Newton meter here, and then when you go to calculate the angular acceleration, you say, well, don't the units work out to just be per second like that, or sorry, per second squared? And the answer is yes. So why did I put radians in there? And the reason is just to remind you that this is an angular quantity. Up to this point in the course, we've been working with degrees for measuring angles because they're the most familiar. But for angular motion, we have to use radians, okay? And you're going to see that in the next few questions why that's the case, okay? Just remember that like one turn or one revolution, synonymous word. One revolution is 2 pi radians, and it's the same as 360 degrees, okay? But for rotational motion, we have to work in radians, and they are dimensionless. It's like if you write it in or you don't write it in, it doesn't matter. It's not really a unit. It's just like a mnemonic device to remind you that we're talking about angular motion, okay? So, all right, there we go. That's the angular acceleration. Let me see if there's any questions so far. All right. Tell me if I'm going too fast. I don't want to waste your time, but I also figure if you're taking notes, I don't want to go too fast either. Okay, so the next question is, how long does it take the rod to spin up to a speed of 30 revolutions per minute? Well, if you reread the question here, I do tell you that it starts from rest. So it starts from rest, and it's going to spin up to 30 revolutions per minute. I'm sorry about that. I hope that wasn't too loud. Okay, so it starts from rest. That means its angular velocity is 0. Okay, so omega naught, the initial angular velocity, is 0 radians per second. It spins up to a speed of 30 revolutions per minute. You got to watch the word speed in English. We use it for lots of different things. Usually when you talk about speed, you're talking about how fast you're moving, like along the road or like along a straight line. And that's a linear velocity. Here, because we're talking about something rotating, it's really the angular velocity. So when we say it speeds up to, or it spins up to a speed of 30 RPM, we're talking angular velocity. But the word speed is like I said, it's ambiguous. I mean, we even talk about the speed of the internet, even though there's like nothing really moving there. So, whenever we're talking about rotating things, when we say the word speed, we really mean an angular velocity. Okay, a lot of mistakes are made just in interpreting the English. Okay, so it starts at 0, it spins up to 30 revolutions per minute, but we have to convert that to radians per second. And so to convert a revolution to a radian, revolutions in the numerator here, put it in the denominator. 1 revolution is equal to 2 pi radians. So this fraction is effectively 1, and it has the effect of converting from revolutions to radians. And then the other thing we have to convert is minute to seconds. So here it is in the denominator, so put it in the numerator here, divided by 60 seconds, and it turns out to be 3.14 radians per second. Okay, so that's what it spins up to. All right, and another thing we know is the angular acceleration because we just calculated it, right? There it is. Okay, so we know the angular acceleration. And I'm asking you, how long does it take? That's t is unknown, okay? And there's no information here about the angle. So I didn't write theta in there, but there's just no information about the angle, okay? I don't tell you that it, like that it turns so much, or whatever. So that's all the information you really have, okay? And you say to yourself, okay, looking at the 3 kinematic equations for rotational motion, which one should you use? And it's pretty obvious that you need the one that we've been calling number 2, okay? That omega is equal to alpha t plus omega naught, okay? And I just rearranged it before plugging in the numbers. So I subtracted omega naught from both sides, and that gives you omega minus omega naught on the left is equal to alpha t. We're solving for t, so I just isolated it by dividing both sides by alpha, okay? And this is the same. I just I just put the unknown on the left-hand side because I don't know. We like to do that, I guess. We prefer the unknown to be on the left-hand side. All the stuff on the right-hand side is known. Plug in the numbers and you get that. And rounds off to 0.080 seconds. Okay, so it doesn't take long to spin up to 30 revolutions per minute. Okay, that's 30 turns per minute. It takes less than a tenth of a second. All right, and that's I mean, maybe I didn't choose my numbers so well, but that's because 30 RPM isn't that fast. But like 100 newtons is quite a bit of force on this rod, which has a pretty small moment of inertia, which is why it spins up pretty fast. But anyhow, that is the correct answer. Okay, so far so good. Okay, E, F, and G, that's where we really have to work in radians. Okay, so the next question I ask is, what's the tangential velocity at either of the tips of the rod once it's spinning at 30 RPM? Oh no! Oh geez. How long has it been since you haven't been able to see the screen? Oh boy, oh boy. I should have looked. I should have looked earlier. Oh darn. We're gonna have one of these days where I'm gonna be losing the screen all the time. It's been a mystery. It's been a mystery all semester long. Why? Let me let me back up a bit. Okay, and the whole question. I'm so sorry, Emily. Let me start over. Okay, so geez, like right from up here from the moment of inertia point. Okay, you know what? Let me go through it very quickly, and uh, uh, I apologize. I'm gonna make it a. I just assumed that that problem had gone away, but it hadn't. Okay, so all right, here we go. Okay, so we have a rod of length 1.2 meters and 3 kilograms. It's free to rotate around the center. Moment of inertia. That's the formula for the moment of inertia rotating around the center. Okay, and it's 1/12 ml squared. Plugging in the numbers, I get 0.36 kilogram meters squared. Okay, now the next one is the torque due to the force. Torque is given by RF sine theta. Okay, and I think this is actually where I lost the screen because that's when I switched back and forth to the other thing. But okay, so it's RF sine theta. R is the distance between the center and where the force is applied. And I didn't apply the force at the tip. I actually applied the force 20 centimeters from the center. Okay, so R is going to be 20 centimeters here. You can see it right there, or 0.2 meters. Okay, the force F is 100 newtons. Okay, and the angle that I'm applying it at, and let me switch back to the whiteboard here. Oh, geez, everything's broken today. Um, where is Pinta? Right there? Nope. There we go. Switching there to the whiteboard, and I'm actually looking at my OBS so that I know that you can see it there. It's being applied at 20 centimeters and at 45 degrees, okay? And it begins to spin about the center, but I'm not applying it at the tip here. I'm applying it 20 centimeters out. So R is 0.2 meters, F is 100 newtons, and theta is 45 degrees, okay? And so here I get 14.1 Newton meters. Okay, a Newton meter could be written as a joule, but we never do that for torques. Okay, just because it looks funny. All right, it's not an energy. All right, next, tau is equal to I alpha is the angular equivalent of F is equal to ma. And I ask you what the angular acceleration is. If you know I and you know tau, you can calculate alpha. Okay, so over here, alpha is equal to tau over I. That's the value of tau that we just found. There's the value of I that we found up here. Okay, and if you work that out, it turns out to be 39.3 radians per second squared. The radians, as I said a minute ago, I just reintroduced it. It's actually not a unit. Okay, and so I reintroduced it just as a mnemonic that we're talking about angular motion, but you could even write per second squared and it would be correct. Okay, how long does it take the rod to spin up to 30 revolutions per minute? Well, it starts at rest, so the initial velocity, initial angular velocity is 0. It spins up to 30 revolutions per minute. Okay, but we got to convert that to radians per second. So to get rid of the revolutions, you multiply by 2 pi radians divided by 1 revolution. Eliminates revolution, gives you 2 pi radians, and we got to get rid of the minutes, so you multiply by a minute over 60 seconds, gets rid of the minute, produces seconds, and that gives you a final velocity of 3.14 radians per second squared. Okay, alpha we found above, and there it is. So that's all you know. I gave you no theta information, that is how much it turned. Okay, and so it's obvious that you just use your second equation there like that. Okay, I rearranged that. Okay, and isolated time, substitute in, and I find that it spins up in very quickly, just 0.08 seconds. Okay, so I think this was the point at which I realized that I had lost the screen. Okay, so let me see here. Uh, all right, Emily, are we good so far? Um, I'm gonna continue from this point here, and I think this should be good. All right. So at this point, I ask, what is the tangential velocity at the tip once it's spinning at 30 RPM, like that? Okay, and just to show you what that means, the tip here, let me switch back to this. So now we're looking at a point on the tip here, and I'll do that in red like this. Okay, now how fast it's moving, I want a linear velocity, and a linear velocity at that point there, that's just like your tangential velocity. Okay, so it's in meters per second. Even though it's going around in a curve, you could still measure how fast it's moving. Even if it's not moving in a straight line, it's still linear in the sense that, like, how many meters is it turning or moving per second. Okay, and so that's the tangential velocity. Obviously, how fast it's moving depends on how far you are from the middle. So you have to picture this bar turning. If you're right at the middle, well then, the middle doesn't move at all, okay? If you're out just a little bit from the middle, like here, then you're moving a little bit as you go around in a circle, but not much, okay? And the further out you are, the faster you're going to go as you go around that circle. Out here, that's when you're going to be moving the fastest, okay? So there's a relationship between VT, R, and omega, and here it is. Here's the formula. Okay, it's this formula right here. All right, I think I'm good up to this point. Okay, I don't think I missed anything. I recuperated from everything. All right, so I can see that you can see it over there now. Yeah, all right, so VT is equal to R omega is what relates the angular velocity to that tangential velocity. Okay, so that there is the relationship. But this formula that you see right there is only valid if omega is measured in radians. Okay. In fact, there's a whole bunch of these not a whole bunch. There's 3 relationships that relate the linear quantity and the angular quantity. And they're related like this. The linear quantity is equal to R times the angular quantity, okay? And we'll see another one of those in a minute, all right? But those relationships that relate the angular quantity to the linear quantity by just multiplying by R, they only work if the angular quantity is measured in radians, okay? Now, the reason for that, you could see if you go back to the pre-recorded lecture, I explain why that works. But basically, that's how radians are defined. Okay, if you use this formula here, but you did, instead of radians per second for omega, you did degrees per second, it wouldn't work. Okay, so that's why we work in radians per second, and that's why I'll insert the radians just to remind us that yes, this is in radians, and we can go ahead and use these formulas. So basically, the radians are critical for these type of formulas right here, where they relate the linear and the angular quantities. Okay, so we have VT is equal to R times omega. R is 0.6 meters. Okay, and omega is we just found it above here. We found it to be 3.14 radians per second, and that works out to 1.88 meters per second. Okay, and again, you'll notice I just dropped the radians. If I just did meter radians per second, you could write this, and it wouldn't technically be incorrect, except that the radians, like I said, it's a dimensionless. It's dimensionless, okay, and so you could just remove it from that, and then you get meters per second, which is what you expect for a linear velocity. All right, so I hope that was a little bit. I hope that was clear. I hope that clarifies things about the relationship between angular quantities and linear quantities, and why we have to use radians for these angular quantities in order to relate them. Okay, here's another one that relates an angular and a linear quantity. What is the centripetal acceleration at the tip of a rod once it's spinning at 30 RPM? Okay, so what's that centripetal acceleration? So the centripetal acceleration, actually we saw that with uniform circular motion, like much earlier on in the course, okay? And I guess that was first test, okay? And that's the acceleration towards the center. All right, I'll draw it in a minute. So centripetal, the petal part, comes from the Latin verb petere, which means to seek out. It actually is the acceleration pointing towards the center, okay? And it's also related to an angular quantity, but it's not the angular acceleration. It's actually related to the angular velocity, but the angular velocity squared. So AC is equal to r omega squared. Okay, and we have r. I mean, I told you that we're looking at the tip, and the tip is 60 centimeters from the middle, or 0.6 meters. Okay, so there's your r. The angular velocity, well, it's the same as up here, okay, in radians per second, okay, but we have to square it this time. All right, and that works out to 5.92 meters per second squared. Okay, and so that's your centripetal acceleration. All right, I'll draw the direction in just a second, but let's do the other one, which is the tangential acceleration. Now, we didn't have a tangential acceleration when we had uniform circular motion, because as long as you're turning at a uniform speed, that's what the word uniform means in uniform circular motion, you don't have a tangential acceleration. The tangential velocity isn't changing, and so it just stays constant, and so there's no tangential acceleration. But here there is. Okay, in generalized rotational motion, your tangential acceleration, tangential velocity can change, leading to a tangential acceleration. Okay, the relationship there is of this form right here. The linear quantity is equal to r times the angular quantity. So here's the linear quantity, tangential acceleration, and it's equal to r times the angular acceleration. Okay, and we're looking at the tip, so that's at a distance of 0.6 meters from the center, and the angular acceleration is at 39.28 blah blah blah. Okay, and we found that up here. Okay, when we did tau is equal to I alpha, we found that alpha was equal to 39.3 radians per second squared. Okay, and so that turns out to be 23.6 meters per second squared. Okay, let me show you the direction of AC versus AT. All right, so back to this. Well, this diagram's getting a little bit messy. Let me just create a new one. Doesn't take that long. Okay, so here's the bar, like that. Let me make sure this is showing up at your end. It is. Okay, good. And here's the middle. Okay, and the centripetal acceleration of a point at the tip. Here's a point at the tip. Okay, the centripetal acceleration, let's do it in purple, will be towards the center. Okay, so that's AC. All right, and that is the one that's given by the formula r omega squared. Okay, this acceleration happens just because that point is moving along a circle. Like if we were to trace out the path of that point, it's going along a circle like this. Okay, all right, and anything that's turning has an acceleration. I mean, you know this, like if you're on a bike or in your car, and you go around a corner, and you go around the corner at a constant speed. It's not like you're speeding up or slowing down, but just the mere fact that you're turning means that you have an acceleration, because an acceleration is a change in the velocity, whether it's the change in the magnitude or the direction. So AC is because of the change in the direction of the velocity. Okay, AT is the other one, and it is in this direction. It is tangential, like that. Okay, AT. All right. And the reason we have a tangential velocity now is because, and a tangential acceleration, is because the tangential velocity is changing. So not only is this thing spinning, but it's spinning faster and faster and faster and faster and faster. Because as you apply that torque, you spin it up. Okay, it starts from rest, and then first it starts to spin slow, and then faster, 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 faster. And so its spinning is speeding up. And so that leads to the tangential acceleration. Okay, so there's two components to the acceleration. If you said to me, well, isn't there just one acceleration? Yeah, you can combine these two into the effective acceleration, like the like what you would really experience. And basically, since they're perpendicular, you would just like add them using Pythagorean theorem. and the effective acceleration would be, oh, that's not very straight. The effective acceleration would be like that, okay? Right there. So that's the actual acceleration is a combination of the centripetal acceleration plus the tangential acceleration, like that, okay? But of course, since they're perpendicular to one another, they're a vector, you add them using Pythagorean theorem. All right. So any questions with that? And if not, we're done with this problem. And I apologize for um, the little blank screen, but I think I covered all the where it went blank. All right. So that whole problem was a combination of tau is equal to I alpha, which is dynamics, and also a little bit of the kinematics, okay? So this is kinematics, and also relating the angular and the uh, uh, linear quantities is kinematics, okay? So let's go on. The last problem I'm going to do is this one right here, okay? And it's actually an angular momentum problem, okay? Now, angular momentum can be pretty tricky, okay? So I'm not going to give you anything more difficult than this, but let's go through it carefully. It's kind of the opposite of the very last problem I did in the pre-recorded lecture, where there I had like a rod and I had this bullet coming in, and the bullet embedded itself in the rod and then makes the rod spin, okay? And what's interesting about these problems, this one's kind of the opposite of that. This one has a disc, and then the bullet gets fired off and it causes the disc to spin, okay? What's interesting about these problems is not only is angular momentum being conserved, but also because the bullet is going in a straight line, it's actually a combination of a linear and angular momentum problem. Okay, and wherever you have angular quantity or linear quantities, you can always convert to angular quantities and vice versa. Okay, so that's what this problem is about. Okay, let's read it, and I'll draw a picture for you as well. So a disk of 1 kilogram, okay, radius of 50 centimeters, is free to rotate around the middle. Okay, so just picture of disk, and got an axis in the middle, and this disk is free to rotate around the middle, but it's initially at rest. Okay, so it's not turning. Okay. There's a little bullet plus a bit of explosives that is attached to the edge. Okay, so you picture this disc, and there's a little bullet and a little bit of explosive behind it on the edge. The explosives go off. Okay, not a lot of explosives because this is a pretty small 5-gram bullet. Okay, and when it does, though, it fires the bullet. Okay, and it fires the bullet at 500 meters per second, and in a direction which is tangential to the edge. Okay, so yeah, well, I'll draw it. Okay, so basically you've got an edge and it just flies off the edge. Okay, so how fast is the disk spinning after the bullet is fired? Remember, it's initially at rest, and after the bullet is fired, the disk is going to spin. Okay, so let's switch back to this, and I knew I lost it, but that's okay. We will. Oh no, is it this one? There we go. Okay. All right, so let me create a new thingy. Whoops. 100% like that. Let me see. Yeah, okay, good. You can see that. All right, so let me draw it. We have a circle, a disk. I'm going to do it in black here. Okay, so here's my disk. Close enough. Okay, and it's free to rotate around the middle like that. And on the very edge, I have this bullet attached like this. Okay, there's the bullet. And I didn't mention this in the problem, but maybe just to help you picture what's going on here. Maybe there's like a little tab here like this that's part of the disc, but between the tab and the bullet, there's some explosive like that. Okay, something like a little bit of gunpowder. Okay, and this thing is initially just sitting there. Okay, so there it is, just sitting there. And what I'm going to do is I'm going to set off the explosives, and the bullet is going to fly off, and it's going to fly off like that. Okay, that's tangential to the circle. I mean, if it went off this way, that would not be tangential. If it went off this way, that would be perpendicular. But I said no, it's going tangential, and the tangent to a circle is like that, right? Okay, and so it's going off tangentially, and there it is like that. Okay, and I tell you, that it's traveling at 500 meters per second. All right, I guess that's pretty fast. But the bullet itself is not that big. The bullet is only 5 grams. Okay, And of course, when that bullet flies off, you can imagine that, that explosives, yeah, the explosives are pushing the bullet forward, but there's got to be something behind it. Otherwise, if there weren't that little tab there, uh, there'd be nothing behind it to push the bullet forward as the explosives go off. And so what will happen is the entire disc will start to rotate this way. Okay, so the disc will have some, whoops, some, oh, try one more time, some angular velocity like that. Okay, and I want you to find that angular velocity. What's that angular velocity equal to? Now, this looks like a really difficult problem to do, and what we want to do is we want to start off by thinking about conservation of momentum. Okay, so conservation of momentum, basically there it is. Sorry, angular momentum. All right, so conservation of angular momentum basically says, whatever the angular momentum is before L, the total angular momentum before, it's equal to the total angular momentum after. All right, so it's kind of like the things exploding and pieces going off linearly, but here one of the pieces is actually spinning. Okay, now initially the angular momentum is 0. All right, why? Well, nothing is moving, and angular momentum, maybe I should just write you the like a formula over here. Basically, whenever you hear angular momentum, you should always think angular momentum is made up of I times omega, like that. Actually, I have it written down here. Okay, right there. Okay, so every time you hear the word angular momentum, you should think I times omega. Like when you hear linear momentum or just momentum, you think that the momentum is m times v. Okay. Now, if you got more than one thing, it's mv for the first one plus mv for the second one plus mv for the third one. It's like you add up all the mv's. Okay. For angular momentum, it's the same thing, but now you add up all the I alphas. Sorry, I omegas. Okay. And I is like m, I is like m, and omega is like v. Okay. So you're adding up all those things. Well, initially, nothing is moving. So there's no omega. Omega is equal to 0. So the initial angular momentum is 0. Okay. By the way, the units of angular momentum are kilogram meters squared per second. All right. Now, after, there are two things that are moving. The bullet is moving and the disk is spinning. Okay. Both of them will have an angular momentum. Now, the angular momentum of the disk spinning, that's kind of easy because you could say, oh, well, the disk has a moment of inertia and it's got some, angular velocity, so it's going to have an angular momentum. Okay, but the bullet is moving in a straight line. So how do you think about the angular momentum for that one? Okay, well, let's look at the disk first because that's easiest. Okay, so the total angular momentum is the angular momentum of the bullet and the disk. Let's look at the disk first. The angular momentum of the disk is equal to the moment of inertia of the disk, I, times the angular velocity of the disk. Okay, and we're actually solving for the angular velocity of the disk. In other words, I ask how fast is the disk spinning after it's fired. So we're actually solving for omega disk. Okay, so we don't want to put a number in for that, but we do want to see if we can get some value for the moment of inertia of the disk. And that's one of these moment of inertia formulas for a particular shape, and it's 1/2 mr squared. Okay, so for a disk spinning around the middle or a drum spinning around the middle, it doesn't matter. A drum is just a disk with some height to it. Okay, or you can think of the other way around. Take a drum and you just squish it down very thin, and it's a disk. Okay, the thickness of the disk or the thickness of the drum doesn't matter. It's just the radius that matters. Okay, so here the moment of inertia of the disk is 1/2 mr squared, like that. And so I tell you that the disk has a mass of 1 kilogram and radius 50 centimeters or 0.5 meters. And so that works out to 0.125 kilogram meters squared. Okay, great. We have the moment of inertia of the disk, but we don't have the omega. So we really can't put in a number for this, but at least we could write this. We could write, take that out and we can put in that number right there. All right. And we can't go any further with that. All right, that's all right. The next one. So far we've only got this, the moment of inertia. Sorry, the angular momentum of the disk. We now need the angular momentum of the bullet. All right. So how do you do that? Well, just like anything else, the angular momentum is the moment of inertia times the angular velocity. But you say to yourself, geez, how in the world am I going to get a moment of inertia and an angular momentum out of this? And let's go back to the whiteboard and I'll show you here. Okay, so um, you could calculate the moment of inertia at any point here. Like you'd say, oh, I can calculate the moment of inertia of the bullet when it's there, the moment of inertia of the bullet there, or whatever. And it would actually be the same value, but the problem is it's really hard to do it there and there. Because remember how you calculate the moment of inertia for a point mass. For a point mass, the moment of inertia is calculated using I is equal to m r squared. Okay, so the bullet is just a point mass. Okay, and I think I did a problem like this in the pre-recorded lectures where I had a child on the carousel. Okay, so it's just mr squared for a point mass. Okay, and m is easy, that's just 5 grams. But you say, well, what's r? Well, if we say, like suppose we wanted to calculate the moment of inertia there, well, then we'd have to find that r there, and that's like a crazy value of r to find. So you know what, don't do it here, don't do it there. Do it right at the instant when the bullet is fired. Okay. And so that is the radius r. Well, you know that radius. You know that r is going to be 0.5 meters because that's the radius of the disk. Okay. So there you go. There's the moment of inertia for r. Okay. Now the next one is omega for the bullet. You go, geez, how do I get omega for this bullet? Because the bullet's moving in a straight line at some velocity. In fact, it's moving at a velocity of, here's the velocity. And you say, well, I've got this velocity, but I need an angular velocity, not a linear velocity. And that's when you realize that there's a relationship between the angular velocity and the linear velocity. And it's this relationship right here, v over r. Okay, so that's just like, let me write it over here. Remember that v is equal to r omega, or actually it was vt, but this is a tangential velocity, right? It is a tangential velocity. Okay, so vt is equal to r omega. So we're just using that, but now we're using it to find omega. So omega is equal to v over r. Okay, and you say, well, do I know v? Yeah, you do. V is 500 meters per second. Okay. And if you're looking right here, if you're looking at just at that instant when the bullet is about to it leaves, or right after the explosion, r is 0.5 meters, and you can calculate it. Again, you don't want to do it out here or out there because then r is some weird value. Okay, and so that's why we look at this point right here. It's not that the angular momentum of the bullet changes over time. It's just that it's easiest to calculate right there. Okay, so my diagram is a little bit messy, but let's switch back here and just go over what I said. Okay, so we're looking at the bullet. The angular momentum of the bullet is equal to the moment of inertia of the bullet multiplied by the angular velocity of the bullet. The moment of inertia of the bullet is calculated by mr squared. M is the mass of the bullet, and that was 5 grams or 0.005 kilograms. And the radius here is, we're looking at that instant where it's still at the edge of the disc. So the radius from the axis to the bullet is half a meter, 0.5 meters, and that turns out to be that value right there. Okay, for the moment of inertia of the bullet, 0.00125 kilogram meter squared. What about that angular momentum? Okay. Oh, geez. Sorry, I meant angular velocity. Okay. So what is the angular velocity of the bullet? Well, that's going to be v divided by r. All right. And again, right at when it's at the edge, and that's 500 divided by. So it's traveling at 500 meters per second, and that's at 0.5 meters. Okay. And so that's 1,000 radians per second. All right. And so we have I and we have omega for the bullet. Putting them together, we've got the angular momentum for the bullet. Okay, 1.25 kilogram meter squared per second. Okay, now we can put this all together because we have angular momentum for both the bullet and the disc. Angular momentum of the bullet, we just found that, 1.25. Angular momentum for the disc, we found that. Well, didn't really find it, but we have it as reduced as possible. Okay, the angular momentum after is equal to the angular momentum before, which is 0. So 0 must equal the sum of the two angular momentums after. And then it's just a matter of solving, and you find that the um, angular velocity is negative 10 radians per second. Okay, so I just left it in radians per second. You could convert it to RPM, but there it is. So is this kind of what we expected? Let's go back to the diagram here. Yeah, and in fact it's negative because it's spinning in the opposite direction to the velocity. Because like um, the bullet, this is getting really messy. Let me just quickly draw another diagram here. So here's the disk. Okay, and the bullet is heading off this way. Okay, and so its angular velocity for the bullet is positive. All right, but the disk is spinning this way, and so its angular velocity for the disk is negative. Okay, as you would expect, because the two, when you add the two together, they're going to have to cancel because the angular momentum before was 0. All right, so that's it for that problem there. Let me switch back to this, okay? And let me see if there's any questions in the chat there. So is everyone good with that? If we are, then we're done with the examples, okay? So just wait a few seconds here to see if there are any questions. So basically with the rotational motion, what you can expect on the test is some rotational kinematics like this, like these type of formulas. Okay, uh, but in addition, there's also the relationship between linear and angular quantities. Okay, and also some rotational dynamics. Okay, that's like tau is equal to I alpha stuff. All right, so you have to know how to calculate tau, the torque, by RF sine theta. All right, and then rotational energy. We didn't do that problem, but we've done it before. Okay, that's problems where like your kinetic energy here, I could just write it very, very quickly, where your kinetic energy is actually calculated using 1/2 mv squared. That's the translational part, plus 1/2, put some space in there, 1/2 I, and let me grab an omega down here, I omega squared. Okay, so and also omega is equal to V over R. Okay, for rolling, for a situation with rolling. Again, we didn't do this, but we've done them. We've done these before. And then, of course, you need to know how to do angular momentum problems. Okay, and angular momentum, like this one, its angular momentum is calculated by I times omega for all the pieces before and after, and they have to equal because it's conserved. Okay. All right, and of course, there's the linear momentum problems as well that we did on Monday. Okay, so all right, I'm not seeing any questions. If everyone's okay, then we can just end the stream right now. All right, all right, bye bye. And again, I apologize for the technical difficulties.